In addition to knowing what integrals are going to result in logarithms, it's also going to be important to know what the integral of a logarithm is. Now, before I tell you what this formula is, I want to go over the proof of what this is really quickly. Now, we know that integrals are linked very closely to derivatives, and so what I'd like to do is go ahead and differentiate a particular function. And the function that I want to differentiate is going to be x times the natural log of x. Now, we would do this according to the product rule. That would be first times derivative of the second plus the second times the derivative of the first. And when simplified completely, this lets us know that 1 plus the natural log of x would be the derivative of x times the natural log of x. Now, by the exact same logic, that also means that if I were to integrate 1 plus the natural log of x dx, that would be equal to x times the natural log of x plus a constant, just through the use of the definition of an antiderivative. However, on the left-hand side, because we have two terms that are added together, I can split this into the integral of 1 dx plus the integral of the natural log of x dx, still equal to x times the natural log of x plus a constant. Now, this probably shouldn't be all that difficult for you to figure out. This would be x plus the integral of the natural log of x dx. Technically, because we did do another antiderivative, there would normally be an additional plus c there, but we've already taken care of the fact that there's a plus c all in all. So, subtracting x from both sides is going to give us the formula for the integral of the natural log of x. This is going to be equal to x times the natural log of x minus x plus a constant. So that completes our proof up here. This would be x times the natural log of x minus x plus c. Now, for those interested, there is another technique for how to integrate this, and it is referred to as integration by parts. This is something that's typically taught in a Calc 2 curriculum, so you will likely see it at that point in time. Now, through a similar piece of logic, the integral of a logarithm of any other base is going to be equal to, for all intents and purposes, the exact same thing. This is due to the fact that if we were to consider the same sort of proof, we would start with x times the logarithm base a of x. We would get first times derivative of the second, which would be 1 over x times the natural log of a, plus the second times the derivative of the first. Now, aside from the natural log of a that we see pop up in here, the rest of this is going to look relatively similar. So canceling those out would let us know that the antiderivative, that's not how you spell antiderivative, the antiderivative, or the integral of 1 over the natural log of a plus the logarithm base a of x dx would be equal to x times the logarithm base a of x plus a constant. Then if we were to anti-differentiate this and move it over to the other side, we would see something very similar to what we just got, and it would be x times the logarithm base a of x minus x over the natural log of a plus a constant. Now again, this is also possible by using integration by parts. It's also sort of advisable to apply a change of base formula to the logarithm base a of x, and we can refer to this as x times the natural log of x over the natural log of a minus x over the natural log of a plus a constant, which would allow you to pull out a greatest common factor of x over the natural log of a. In fact, you know what? Let's do that down here. I'll bet it's going to look considerably prettier. So this is going to be equal to x over the natural log of a times, we'd be left with the natural log of x minus 1 plus a constant. Yeah, you know what? I regret nothing. It does look considerably nicer. Yeah.